All right, guys, let's get started. So we are now recording. Okay. So you guys are section two. Uh, section two. So just a few reminders. I think the homework assignment for pre-training the LLM is due a week from today, right? So remember, you will be presenting that assignment in class. So you'll bring your model and you'll show what you did, how you trained it, and we're going to ask it a few questions, things like that. Any questions about that? Not really. I mean, it can be informal, but just have the substance, right? That's what matters. Yeah, I think it says on the description that you should use both methods. Try them out. You can take a look. Use tick token and the letters approach as discussed in class. So try both of them. It's really you should notice something interesting, right? So that's the idea. And remember, the goal is to train with as much data as possible, even though, of course, you're constrained by your resources. Anything else? Hmm? Mm-hmm. Yeah, I just need a report. You think about all these things, when somebody did the transformer or something, they don't give you the transformer, right? Everything we get is through reports, papers, and you can follow the links into that. So all I need is a report, essentially. Anything else? No? All right. I think I finished grading your exams. So those are done for this section for sure. So you can look at those, and then you'll have that homework assignment. And definitely, we have a tight schedule going forward, so I can't delay that. All right, so that's homework 2. Homework 3, I'll be creating in the next few days. It'll be related to the topics we've been covering since last week. If you notice, during this second third of the semester, we're going over type regression classification approaches. So the homework will be just, although I haven't created the link, it'll just be find 2 data sets, one for classification, one for regression, and then build the corresponding models, train and test. Does that make sense? So that's it. That's what the homework will be. But I'll, of course, create a description. You don't need as much time for that one. So I'm debating whether it's going to be a week or 2 weeks away at most. Okay. Yeah. And so what I did last week and what I'm doing this week is a very important foundational part of the course, right? So hopefully you all went over Iris, right? So we went over Iris, we went over that classification, and everyone understands all of that. So as you can see, even though maybe the first third of the semester every day it was something new, now it starts to get a little bit repetitive, right? You start to see the same things happening. Hey, here's that class. Hey, here's this loss function. Everything is starting to become repetitive, and that's how it is with machine learning, right? So once you get to a certain point, you're just repeating things. In fact, I've said many times, it's like you have a toolbox of 30 or 40 algorithms, and that's it, right? That's it, honestly. And then everything else is your skills of converting the data into the CSV model, the vector space model, and that's it. All right, and knowing when to use what. So yeah, so you guys are section 2. So let's kind of remind ourselves where we are. So let's go back to table of contents. So we've completed all these modules and we are here. Okay. So in the next couple of weeks, like next week, I'll go over performance metrics. I'll start diving into the loss functions a little bit more. Cross entropy is the next one for me, which I want to cover, which I think, yeah, for some reason, I have it done. I knew I had it down there. So somewhere around there. So cross entropy certainly is coming up. It's very nice, right? MSE, I think, the other loss function, is easy. You probably already looked at it. If you've taken a stats course, you saw it there. So we're going to see it again, obviously, in a more vectorized tensor-based approach, and cross entropy comes from entropy. So it's pretty interesting there. So yeah, so definitely we're diving into some of the theory of training, right? If anything, during the first third of the semester, it was mostly inference. That inference function, remember that there's essentially two equations, the inference equation and the loss equation, right? And so now we're diving in a little bit deeper into these loss functions and just creating neural networks. All right, so we are here in this module, your first neural networks, and today we'll wrap this up essentially. Remember, I provided reading materials, so hopefully everyone has started reading these, right? It's very important that you read these materials. I provided the notes, chapters 2, 3, and 4. So you click on these 2, 3, and 4 in blog post type format. And also they're provided in a PDF type format in this document. All right. So either one, read both, it's not going to hurt you. And this is, the details of what we're talking about now. Okay. So now we're going to go to the code today and just see where we are. As these are, I think, very important pieces of code. In fact, I should say, so if there's one thing that you take away from this course, right? And there's a lot of things that you should take away from this course. But if there's only one thing, it should be this. Okay, this is the one thing that, it's the very basic entry level, but also quite useful. All right, so last week I started with Iris, so the Iris CSV, and we went over this script, classification Iris. Next week, we will cover this script, cross entropy. All right, and that'll conclude our discussion. And today we're going to focus on these two scripts. We're going to be using the wine quality dataset. So I'm using a different dataset now from Iris. So this is more of a, imagine yourself working for a company that sells wines or makes wines of some kind, right? So one of the things you'll want to have is some kind of a measurement of quality. And that's going to be based on some variables about the wine, right? The acidity, all those things. So essentially, this data that we have is about that. People have measured several variables and have given a score for the wine, right? And so what's nice about this data set is that we can use the same data to train either a regression model or a classification model. And so that's kind of my plan for today, is to go over both of these examples, kind of run through the data and learn that task. Regression problems are very common. As I mentioned before, you go to some organization, they have Excel spreadsheets full of things that they want to predict. Usually regression values is a more common thing than them wanting you to classify something. All right, so definitely we want to be able to do regression, and so we can talk a little bit about it. All right, so it should be this one that says regression. I also use a technique called XGBoost, and that's just simply because even though neural networks are extremely powerful, whenever I'm dealing with regression and tabular data, XGBoost is always like one of the best methods. And it's a non-neural network method. In fact, it's a decision trees method. So I'll throw it in there for comparison. And definitely whenever you do something in regression, throw XGBoost at it. You will not regret it. All right, so this is going to be our script, and our data set is going to be the wine quality white.csv. Okay, so we're going to switch over to Colab and just use these, proceed with them. So obviously, as I do with anything, somebody gives you data, the first thing you start doing is trying to look at this data, right? Let's get a feel for the data, what's going on. And from there, we start to develop a picture. So I'll start with regression first. I'm going to need, of course, Colab here. Just makes it easier. Sorry. Sorry, guys. I've had a bad cold. All right. All right. So here we are. And we're going to need the data set, which I already have in my drive. I already added it. So if you remember from the last time, so I'm just going to mount the drive. Okay. Okay, so it should be in here. So we're just going to copy where it is. It's the wine quality data. So if you guys see it, let me know. Here it is, wine quality CSV. So we're going to copy the path, right? Just down here somewhere. All right, so this is going to be our data set. We have our Jupyter, our Colab here, and we just need CPU for these. This wine quality data set is a little bit bigger. We're going to see that. I can't remember what it is, but we're going to establish that in a second. But like I said, regression stuff in companies is usually very small data sets. Okay, so let's proceed with the libraries. So I'm going to bring in libraries here. So the usual suspects, right? So pandas, torch, numpy, sklearn, and then the ones that do the heavy lifting for us, torch NN functional, and optim, right? So the optimizer. Same thing as before. We brought those in. And yeah, so one thing I still need to do next week is I need to do the Onyx deployment. If this code has it, I'll show you guys how that's done. All right. Any questions, guys? No? All right. All right. So let's bring in some of the other libraries. MXL extend. I like this library because I like to do the correlation matrix, right? So that's very useful. We're going to be creating data loaders, torch tensors. So as I said, it's very repetitive, right? I'm literally doing the same things from last week, but there's always these subtle differences that we have to pick up on. Notice the metric, for instance, I'm going to be using from sklearn the R-square metric. All right, so this is a different kind of a metric when, from the classification metrics. This is the one I like to use, which is regression, because this is what people want to see. They're used to this metric. They've seen it many times, and when using software, so they'll understand it. All right, so we've added the libraries here. Yep, there we are. And then let's add XGBoost this time. We do need it today. So if it's not installed, we're going to have to install it. But we do have it available. If you don't have it available, something like pip install will do it for you. So XGBoost, as I said, is a machine learning technique, but not a neural network-based machine learning technique. And instead, it is one based on trees, decision trees, and things like that. And then let's bring in the Onyx tools, since one of the goals for that homework 2 will be for you guys to deploy those models. All right, so let's see here. All right, so this is the same issue as the last time. Need to install these 3 libraries. So Onyx runtime and Onyx tool. Let me just do it here. All right, so pip install Onyx runtime. Okay, so that's installed in Onyx tools. Since you're going to be using Onyx for the homework and for some exercises, um, one thing to be able to deploy that Onyx model, we need some kind of a web hosting environment. So I usually use GitHub Pages, which is a feature in GitHub. So that's what I recommend. So if you don't have a GitHub account yet for some reason, I recommend that you go ahead and create one and have that available for the next class. So going forward, we're going to want to use GitHub and GitHub Pages so that you can deploy your models. All right. So make sure to do that. All right. So I've added Onyx tools, and I think the last one should be this one, SKL. This SKL one is, as the name implies, is related to sklearn. So as you can see, as I've been saying with regression, that we can use neural networks, but also XGBoost. So XGBoost, it might turn out that the model for XGBoost is better than the neural network models. So in that case, we would want to deploy that model, right? And so that's what SKL to Onyx provides. It just gives you a way to have a type of a sklearn pipeline that is deployable. Okay, so that's what the library is for. So in essence, we are able to deploy either Torch neural networks or XGBoost models to the web. All right, so all of this should be available now. So I'm going to go ahead and comment this out. Okay, now let's try these three again. All right, and they're available. Perfect. So I think we have all the libraries and we're ready to go. Now the same thing as before, the parameters. This should be pretty familiar to you now. So we need a batch size. We're always going to have batch sizes because we have the possibility of using a GPU. So you want to efficiently use that GPU by providing multiple samples per batch. The learning rate, you can see this one is 0.005. You can play with the learning rate, 0.003, something like that. I mean, you could try smaller learning rates like 0.03 or smaller ones like 0.00003. So this is something that, in essence, in general, if I'm doing one of these problems, this is where I will start. But this is not where I may end up, right? And sometimes you can have variable learning rates. So these are the learning rates that over time, as the model is learning, the value can change. And those can be very useful. But we'll see how to use those later. And it's not really that hard. It just adds more code, which is the problem when you're learning in the beginning. Number of epochs here, I'm going to keep it at 100, but this is a parameter we can change. Remember, in essence, number of epochs just means this is the number of times that we give the whole training data set to the model, right? So we just repeat that process. And epsilon, you have seen me use this for the normalization before. So we've got our same parameters, nothing different. All right. Now I think we start going into the data, and this will be different, obviously, because it's a different data set. So I'm going to read in the wine quality data set. Again, I'm going to use my preferred methodology, which is to use pandas to go from the CSV file into my environment. So I want to create a pandas data frame, allows me to play with the data, modify it very efficient. I mean, you could spend a semester just learning pandas. Okay, so pandas is very powerful, but it has a lot going on. All right, so obviously here we're going to change the path to be the one from our Google Drive. All right. So here's the wine quality data. I don't know if it's a comma separated. I believe it is. Okay, so it didn't like that. It may not be. I think it's this D, right? I don't know where that came from. Let's try it again. Okay, so we've got it this time. So it's probably a comma separated file. And now we can just look at the data, right? So the first thing we want to do is we just want to get a feel for the data. All right, so that's the next step. Usually we want to look at the pandas data frame. This provides a lot of information for us on what we're doing. So let's see. We have a pandas data frame. It says that it's 4,898 rows and 12 columns. Okay, so that's pretty important. So I'm going to, when I do the train test split, I'm going to use 80% cutoff. So that means about 4,000 samples for training, 1,000 samples for testing. That's a good data set right there. Very good data set. Okay. And then we have 12 columns. And so now you can have multiple input, one output regression models, or multiple input, multiple output regression models. Do you guys understand that? So you have a vector of 12 going in and it predicts 3. That's multiple outputs. Or you have 12 going in, but it only predicts one regression, one value. Okay. So in our case, we're going to do multiple input, single output. But you can, of course, for regression, build those kinds of models, multiple input, multiple output. Usually, a multiple input, single output is in general going to be better than a multiple input, multiple output, just because let's say you have 3 outputs, right? So to improve the performance of this one, the weights have to change, which may affect the performance of the second one, right? Or you improve the first one, and that may affect the third one. So you end up sometimes with that little problem. However, if you're working for an organization and they have 40 regression predictions, right? Taking that approach means that you have to build 40 independent models. Do you see that? Where if you use multiple input, multiple output, you could have just built one. So it just depends, right, on what they want, and it depends on the performance. But in general, the single output, so in general, the single output might have like a 90% R square, a 0.9 R square. And then with a multiple input, multiple output, you might be at 82. So the performance does go down, but it's still good enough in some use cases, especially if you don't want to have to create 40 models every time. Does that make sense, guys? So so that's something that I have observed. So single outputs just allow you to squeeze, you tighten those weights just a little bit more so that the scores are better. But it just depends on what the client wants. All right, so let's take a look. Oh, I'm sorry. All right, so let's continue analyzing our data. So the wine quality data, we know we have 5,000 samples. So we'll use 4,000 for training, 1,000 for testing. We have 12 columns. So we need to identify, first of all, the target column. So that's going to be quality. Do you guys see that? The wine quality is what we're trying to predict. So the inputs are going to be these variables. So the acidity. So actually there's a fixed acidity, volatile acidity, citric acid, residual sugar, chlorides, sulfur dioxide, total dioxide, density, pH, sulfates, and alcohol. All right. So And this is very common for these type of regression problems. They're usually some kind of a chemical or something kind of a process in some business, right? Where they're making, something wine, or they're making some material that they're selling, right? So they want to calculate the production rate or things like that. But in this case, we are trying to predict quality. So this is a range of values that's going to go probably from 0 to 10, right? It's a scaling, but this is a regression type data set. A more regression output would be, for instance, if we were predicting values like 32, 37, 35, 45. The quality values here are a little bit more discrete as they increment by 1, so they're not real valued numbers, right? So usually the description of a regression type of problem is that you're predicting real valued numbers, right? These are not quite real valued numbers, or more discrete numbers, but they're still within a range, and there's plenty of them, right? And they're not categorical, where a 2 doesn't necessarily mean more than a 3, for instance, when we're trying to predict classes, right? So in essence, in that case, in that regard, these are regression type values, and you can see them here. So this is the model that we're going to build. So the first thing we need to identify is how many values we have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's going to be the input vectors are going to be of size 11, and the output vector is going to be of size 1. 1 neuron for the regression. And what's something else that you should notice immediately about the data that needs to be addressed? So if you notice, the data needs to be scaled, right? So they're not in the same ranges. This one's around 7, 8. This is decimal 0.20. This one's in the 45, 47 range. So definitely a lot of differences. This one goes up to 170. So you do not want to keep these on normalized, but as I've said many times, you should always normalize your data. All right, so that's going to be one of those steps, but you're actually already familiar with that. So let's go ahead now and continue. All right, so we want to do the correlation matrix. Okay, so the same approach I usually take from the pandas data frame. I'm going to grab all the headers, and here they are, quality, etc., all of these. And if I just want to focus on a few of them, I can just remove them from the list. All right, and then we're going to pass this list onto NumPy to calculate the correlation. So here's an example, for instance, if I just wanted a few of them, density, pH, sulfates, alcohol, and quality, just 5 variables. So you just create a different headings list, okay? But now we do the correlation matrix, and this is the kind of thing that people would be very happy to see, right? So you'd be amazed at how many smiles you get when you see this one, right? The correlation matrix. Essentially, you're just comparing the quality to all the other variables, right? And the key thing that you don't want is you don't want to see zeros here, right? So here we're comparing quality to all these variables, so you don't want zeros. You want some kind of correlation, either positive or negative, it doesn't matter. The stronger, the better, right? So in this case, this is a nice example. We can see, for instance, that the strongest correlation to the quality is in relation to alcohol, right? So alcohol, you can see, has a 0.44 value, and it has the highest positive correlation to quality. That means people are saying, somewhat more alcohol equals more quality, all right? A negative correlation that's also high is density at minus 0.31. There's another one at minus 0.21. In fact, a lot of these are negative, right? So the quality improves as these values go down. So as the density goes down, as the sulfur dioxide goes down. That sounds about right, right? Chlorides, sugar, I guess. You don't want it to be sweet, and so on. Does this make sense? So some of this is chemical, but it's intuitive for us to kind of, yeah, something being acid, right? We don't want that probably. So you can see it's got a minus negative 0.19. So this already tells you a lot about the data, that it makes sense, right? And this is essentially how it works. So now we build a model for this, all right? And we're going to talk about, because we're building a regression, the other type of loss function that we use. So far this semester, at the LLM and with the Iris data set, we've been using cross entropy, right? And now we're going to be using the MSE, the mean squared error, which is a very intuitive type of loss function. You'd be surprised to know there's really just two loss functions, right? There's a lot of variations of them, improvements, the Huberman one or whatever, right? But they're always just kind of the same idea, extended, constrained, and somehow, right? So that's what's really nice about machine learning, right? So inference, a lot of research goes into that, and people are constantly inventing new inference techniques. But when it comes to training, when it comes to these loss functions, it's like this was invented 30, 40 years ago, and they haven't really changed it. Only one algorithm to train, stochastic gradient descent. And within that, the functions that we use for the loss optimization or the goal of the optimization are MSE or cross entropy. Cross entropy for classification, as LLM was about choosing tokens. That was a type of classification. Iris was about selecting setosa, virginica, versus color, a classification. Today, a regression type of problem with MSE. All right, so we've done the correlation matrix. Now we can proceed to take our pandas data frame. We're done with the analysis, or no transformations required. Now we're just going to convert it into NumPy and Torch tensors and start that whole process, right? Of arriving at our X and Y so that we can, do the training and build a neural network. All right, so let's go ahead here. Copy this one. Okay, so we're just going to convert the pandas data frame to NumPy. Again, it's exactly what we were doing before. So, it starts to get repetitive, which is nice. We can look at the NumPy tensor. There it is. Add a few more. Now, usually I live by the shapes, as I said. So I like looking at these things. 4,898 samples, 12 columns. The last column is the quality. So we're going to need to slice that out to create our X and Y. All right, so we can do that with this code. We've been doing this since the beginning of the semester. So X is going to be all the first columns, and then the last one is going to be the Y. There we are. So now we have our X and our Y. We can view it. So for instance, I'm going to print these. You can see now we have two tensors, 4,898 by 11 and 4,898 by 1. And that's it. If you remember, in the last time, we converted the y's into integer. But in this case, we actually may not want to do that because we're doing regression. You see that? So here's a subtle difference now. All right. That shouldn't be a big deal because, PyTorch can handle it, but just more correct. So we can take a look at the y vector. And you can see those are the labels. Okay. So now we can proceed to do the train test split. In this case, I'm once again doing a random seed so that every time that I run this Jupyter Notebook, I get a different split, which might result in a different R square. If I repeat that 10 times manually, I can average those R squares and kind of get a good sense of where my data is without having to write a lot of code, right? So this is a simple approach. So notice here, just random seed. And now I'm going to proceed to do the train test split. Notice that I didn't do a class imbalance analysis. Why didn't I do that? Because it's not a classification problem. It's a regression problem, right? So I could have done it, and we will do it in the classification example just because it's important. But since it's just one neuron, right? That's the output. We don't really need to do that. All right, so now if you notice the exact same thing, I've literally haven't used another way of splitting data for like 10 years or so. So I use this all the time. Train test split from sklearn works really well. Same idea as before. And now I have my tensors and they're ready to go for training and evaluation. Okay, I can print the shapes now once again. And you can see now I have 3,918 samples for training, 980 samples for testing. This is a pretty good size data set, I think. So if you, for this type of problem, so doing 10 different splits and getting a good set of scores here is pretty significant. All right, so now let's once again the same thing. We can look at the data types. We can look at the data types just like before. And we've talked about this already. Quantizing. So you can see it's a float 64. So some of these we might want to change to float 32. So pretty consistent. So I'm going to convert them actually. I'm going to convert them to float 32. All of them, really. Okay. Well, they're now all float 32. And then I'm going to convert them from NumPy to Torch tensors. So now we're done with that processing. We've created our data set, train and test, X and Y, and we're ready now. I did everything pretty much in NumPy, and now they've been converted to Torch tensors, and we are ready to start creating our data set. So notice the same set of approaches or set of steps. First, we create the normalization once again, because we might want to deploy these models to the web. We want to do the scaling inside the neural net, but we just calculate the means and the standard deviations of the data outside. And then we're going to pass it to the neural net as a constant. This is the exact same thing we did for Iris. In fact, I almost always do this. Okay. Later on, you're going to learn about batch normalization and things like that when you normalize from one layer in the neural network to the other. Remember, there's two types of scaling: normalization and standardization. Normalization from 0 to 1, standardization from like -2 to +2. And I'm using standardization. Okay, so I'm going to go over here now. So notice from X-train TR, I take the mean, and from X-train TR, I take the standard deviations and produce these vectors X means and X deviations, which I will pass to the neural network. So we can take a look at X means, and let's see what you guys interpret. So Here it is a vector of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Why 11? 11 features, right? We have 11 features exactly. So for every column, we took the mean, mean, mean. Got it? And then we do the same for the standard deviations. And then that way we have a simple equation that allows us to scale things and descale them, right? As needed. So remember that I've kind of, the way that I'm suggesting this is people, if you're deploying this for someone, for a user, they want to enter the values in the real scales because that's what they know. And then you're going to normalize it inside the neural net. All right, so we've done this part. Let's also print out the standard deviations. So X deviations. And there we are. It should be the same. 11, I think it was. And so we should be ready now to start creating our data loaders. Data loaders should be a really great thing. You just have to make sure that they're in a specific format. So here, if you look, the way that we have the tensors, this is another way, a little bit different from how we did it on last Thursday, right? For the iris data set, what did we do? We created a list of tuples, if you remember, where we made sure that the input was a vector and the output is just a number for the classification. And then we were able to directly load that into the Torch data loader. This is a slightly different approach, but also works. So notice we're going to use tensor data set first to format things into train DS, and then train DS will be passed into train DL. What's key here is to know the shape of X train TR and Y train TR before we feed it in, right? So that way, if you're doing this once again for another data set, you just have to make sure that that data set matches this one. Got it? So let's first print out the shape once again of X train TR. So actually, let me grab. So I'm going to use tensor dataset. Tensor dataset is coming from the libraries. Okay. But I want to print the shape of X train TR. So I'm going to do dot shape. So notice it just needs to be a torch tensor of number of samples by the number of columns. Okay. And the same for Y train TR. Dot shape. And that gives me 3918, comma 1 for that regression value, which is the quality data. Got it, guys? So with this approach, you take the two tensors, run them through this class tensor data set, which creates your train DS, right? And then this train DS now will go into the data loader. And that should be it. So we grab the data loader is similar to what we had before. Notice we want the data to be fed in batches. So we have 4,000 samples in the training set. So it's going to randomize them and then grab 16, then 16 and 16 and 16, right, in batches and feed them into the GPU. Got it? Or the CPU, whatever you're processing. That's the batch size. And we also want to shuffle them, right? You see that? So, yeah. So hopefully all this is starting to become familiar, even though it's only your second time. So now imagine when we're in like week 10 doing CNNs, we're still going to create a data loader, right? Where we're still going to be creating these things. This pipeline does not change. I mean, there's new modules or components, but we follow these steps almost like a recipe. All right, so train DL has now been created. So there you go. My data loader is created. Perfect. And train DL is an object, obviously, from Torch Utils is a data loader object ready to go. Okay, we did that for train. Later on, we might do that for test. But now if you notice here, we're also ready to start thinking about the neural network architectures, okay? Remember, this is a regression type of architecture. So I will point out the very subtle differences between classification and regression. So here I'm going to do four different architectures, okay? We're going to look at four different neural network architectures for this idea. So let's start with the simplest one, which is linear regression. And, linear regression is essentially something that you may have studied before in a stats class, I'm sure. And maybe you never realized that it is, in essence, a neural network. It's a linear neural network, that doesn't make sense, but it's a non-linear neural network. Or, basically here, because the thing is neural networks are essentially regression models, right? But they have to be a neural network, we have to have activation functions such as ReLU, GeLU, etc. So this one does not have it. So we'll explore it. Anyway, let's start with this one. We'll do all four for this one. So let's start linear regression. So, and as I said, you may have heard of linear regression. You were just learning some way, right, to build a line or something like that. This is a linear model, but we're going to write it in the style of neural networks in PyTorch. And that's the key thing. Once again, we are back to that same recipe of before. Whenever you want to create a model, we use a class. So here I'm calling it linregnet. Remember, it inherits NN module, right? Within that, you can have as many functions as you want, but at least two. I have the first one, right? That constructor, which is def init. And I have the second function inside, which is the forward function. So if you remember, this is the approach we took even when we created the large language model. So what do we do here in the init? This super init just initializes the inherited class. Notice here in the constructor, whenever we instantiate, we provide the x means and x deviations. So those are for scaling and standardization, just like we did before. Remember that in init is where we define our variables, right? That we will use later to build our architecture in the forward function. So here we assign x means and x deviations, and we use the famous now nn.linear, right? So everyone should know. So it's a question on the exam because it's so important to understand it, right? So nn linear, which allows us to create from an input to the next layer, right? Via matrix multiplication, that mapping. And we're just going to call it linear one. So a linear regression is essentially just this, right? So this is better understood by creating the neural net. So we'll do that in a second on the whiteboard. And then here, notice when we create the forward function, we got an x that comes in, that's the input. That gets what? Standardized, right? So we standardize it. And then that x goes into linear one to produce ypred. And then ypred is predict. Do you guys see that? So this is the very first one. So let's now go to the whiteboard and let's just imagine this architecture. Okay, so we're going to go to the whiteboard. Okay. So what did that linear say? So linear one, self dot linear 1 was equal to what? Was equal to nn dot linear 11 comma 1, right? So essentially what this means is we have an input layer dot dot dot, and this has size 11, and then the next layer only has one neuron, and it's the output. There is nothing else in here, no other layers. Okay, notice there were no activation functions either, right? There was no softmax. Remember, I would denote things like softmax by adding this square. There's none of that because softmax, we're using it mostly for a classification, right? So that's one thing to memorize. We use softmax for classification, but this is a regression. We don't want to map these values. Remember that what those things like ReLU, GeLU, softmax, sigmoid, what they do is they'll take a number that might be 32 and map it to a scale between 0 and 1 or -1 to +1 or something, right? So they'll convert 32 into 0.6. That's what those things do. But here we don't want to change that necessarily, right? And so here we just want to predict the value from 0 to 10, correct? So we want to know if the wine quality is a 7 or a 5. So there's nothing to run it through. Do you guys see that? Any questions? All right, so that's the architecture. So how do we go from here to here? Why is it a linear regression? Because we learned that linear regression was something like W1, X1 plus W2, X2 plus dot, 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 Wn, Xn. Maybe in your stats class, you even did a thing where you actually could say, what is W2, W3, given the parameters, right? You did something like that. You can actually do an analysis of the variables of the weights. Well, you should be convinced that that thing that you did in linear regression is exactly the same thing we're doing here. It's the same architecture. We take our vectors times some kind of a weight matrix, right? Let's call it W0, made up of all of these, right? These are these values here. So taking, and if we denote this as X, so X times W plus the bias will give us O, which is this one, the output. So it's essentially a simple regression, and this is how we have written it without any activations of any kind. All right? So it's because of the lack of activation, it's not really a neural network. A neural network needs to have nonlinearities, which are provided by those activations, but essentially that's the only difference. Make sense? So, yeah. All right. So you've started with the most basic model, right? Just a linear regression, and you can model that easily with PyTorch. All right. So we did that one. Go back now to the screen here. All right. And what I think is what I did the last time, I do just one model, look at the performance, then I'll do another architecture, look at the performance, and that, makes more sense. So I've done a linear regression here. I have a trained DL, and there you are. So I have linreg net architecture established. So this would be now in terms of how powerful this architecture is, this in theory is the least powerful, right? This is the weakest, in fact. But for many years, prior to 2010, people were trying to solve things with linear regression or regression. All right, so I'll skip these as I said for now. And now let's go to our very familiar training function. So now, same thing, right? So almost the exact same training function that we use for the LLMs. Now we're back